YouTube, another video, and this time I've decided to explain about the 555 timer. Not in a sense of how it works, but more how you work with it and what is its function. So just in a nutshell, so you know how to use it and how it works in different circuits and how people utilize it in different circuits that you see. So just to start, everything I have on the breadboard is all 555 timers, just set up in a standard configuration. You can find it in the data sheet for a stable and monostable modes. And we're going to start by looking at this little circuit here, which is not a 555 timer. It's a binary counter, a C4520, a dual binary counter for that matter. And I've set it up here, and this will be the point where we're going to start with the explanation, where I've set up this binary counter, and I want to count just a single step, increase the value in a single step. And what I did to achieve that, I took this switch, and I've connected the switch to the positive through this resistor, and the other end is connected to the clock pin of the counter, of a single counter. And we have a pull down resistor here to give a low to the clock pin. And I have the switch again. I want to count a step forward, so I'm going to put the switch to high, and you see that something happened here. The lights have changed in a certain way. But that's it, it just stays in this mode. It does that because right now even though I've set the switch to high, it's not the way that the chip will work. So it has progressed a count, let's say, forward. And right now it's waiting to receive a low in the clock pin so that the clock pin can reset. And then on the following high, it will again go a count forward. So once I lower the switch, nothing has happened, and once I raise the switch again, then again it moved to a different value. Now you already saw it right now that just when I do this, I get this random results, and that's because this mechanical switch is not really the way that you need to be working with the clock pin on a chip. There is a certain, let's call it, gray area between the on state and the off state, where we have no control over the voltage that goes into the clock pin, so that produces erratic behavior. So at this point, if we want to utilize the counter in an efficient way and just count step by step, we need to have some sort of a more stable and efficient mechanism of switching on and off. And this is the point where the 555 timer comes into play. And from here on, we're going to discuss it, and we're going to see exactly what its function is. So I'm going to remove the switch, put it aside, and we're going to look at this first example that I've set up here. And it's a 555 timer in a monostable mode. The timer has two modes of operation. It has monostable and astable, and you don't need to think too much about these terms. I'm going to explain it also later, but to make things simple, monostable mode is basically where the timer will wait to receive some sort of an external signal, whether manually, like pressing a button, or from an external circuit or device that is connected to the trigger pin on it. And only when it receives this input, then it will produce a single pulse, and it will go low and wait for the following input to come in. So I've set it up here to produce a pulse for every 2.2 seconds. And here I've added a trigger pin which receives a low, and it has a pull up to high, and a button, once I press the button, you can see that it generated a pulse, 2.2 seconds, and then it went off. And if I press the button again, then again it generates the same pulse and then it goes off. And if I press the button repeatedly, it will generate the same pulse, 2.2 seconds, and then afterwards it will generate another one, but it won't turn on and off at the rate that I'm pressing the button. So to demonstrate this, I'm going to take the output pin of this monostable timer, and I'm going to connect it to the clock pin of my binary counter. And this time I'm going to press the button. It generated a pulse. The counter went up only a single count. It has increased by 1. And I'm going to press it again, and here it increased by another 1. And I'm going to press it again, and we've reached 8 and 9 and 10. But if I press it repeatedly, you can see that the counter will just progress at the rate that the timer generates the pulse every 2.2 seconds. And we can configure it in any way we want, any timing, 2 seconds, 1 second, 1 millisecond. It all comes to the values of the resistors, R1 and C1, the capacitor here. And there are ways to calculate it. You can go to Wikipedia and find formulas there, and you can try it yourself with pen and paper. But to make this explanation easier, I'm going to show everything on just a calculator which you can find online, or you can also download it, and I'm going to show it here on my mobile phone. I hope that it will show good on camera. But what I did, I have here 2 resistors in series to produce a 2 mega ohm resistance. First I'm going to set my calculator to monostable mode, and R1, which are these 2 resistors in series, I have 2 mega ohms. And my capacitor is 1000 nanofarads, which is good. It's 1 microfarad. And we want to calculate the pulse time, and we receive 2.2 seconds. And that's what the length of the pulse that is generated here. And you can see again that no matter how many times I press it, it will always go only 2.2 seconds. That's the pulse that is generated. Moving on from this example, we're going to look now at this section here. I have 3 555 timers, and they are set to a stable mode. And the difference between a stable mode and monostable mode is basically that you can say that the timer sort of triggers itself. So the circuit here is made in a way that it's configured in a way that the timer charges and discharges in an oscillating way. So it continues to provide the same signal each time, repeatedly, and it will produce it accurately and a stable signal. When we talk about a stable mode in comparison to monostable mode, we no longer define the signal that is coming out as a pulse, as in monostable mode. We define that as a frequency. And to explain that, when we use monostable mode, we define here the circuit to provide a pulse of 2.2 seconds, for example, and it will produce that pulse for 2.2 seconds. The signal will be high, but after that, if there is no more input into the trigger, it will just go low, and it will wait until the next input will come in. And if there is an input, then it will just continue in this cycle of every 2.2 seconds producing a pulse. So we have no control over the time that the timer is on low state. We have no control over the low state, only on the high state, where with a stable mode, we're not only defining the time that we will have a high signal, but also the time that we have a low signal. And those two periods of time together, the time that we have in on mode and the time that we have in off mode together, they make a frequency. To explain that, I've made a little drawing here on paper. And we're going to look at each one of these timers. Now, first thing, all of these three timers, you can see that they pulsate in roughly the same rate, and that's because I've configured them to work in the same rate. They all work in a frequency of around 1 megahertz. So this one is 1.2 megahertz, and this one is 1.1, and this one I think is 1. And you can see that they pulsate in the same rate and roughly once per second. But you can see also that the LEDs, they light up differently. That's because in the frequency that we generate with this stable mode, right here, you can see the entire cycle. So the off time and the on time together, they make a single unit within the frequency of these timers. They work, let's say, on 1 hertz. That's roughly the values that I've set. And at this point, we add another term, which is called a duty cycle, and that comes as part of the frequency. And a duty cycle means how much time within this whole cycle the LED or the signal coming out will be high. That is the duty cycle. So let's look at the first example. We're going to start with B here. And you can see that B, in comparison to A, the on state is longer and the off state is shorter. Where A, the on state is just momentarily, and we have more off state in it. So if we look at B within this frequency, the duty cycle will be 54%, and that's the on state, and the rest 46% will be the off state. And that is how we see this indication on this LED, where we have roughly the same time of on and off. If we look at example C, we see that the LED is most of the time on with just a fraction of a moment that it is off. And it has a duty cycle of 92% and 8% time that it will be off. And example A, we can see it right here, the way I've drawn it, is that the duty cycle in this one is 23%, if I remember correctly. And this is what we see. We see a short 23% of the cycle, of the time in the cycle it will be on, and the rest it will be off. So just to demonstrate how I've reached these values, again, let's go to the calculator. And this time I'm going to set my calculator to a stable mode. I'm going to start with example B, where I've placed R1 as 100k resistance, and R2 is 560k, and we have a 1 microfarad capacitor, and we see that we produce a frequency of 1.1 hertz. That is a bit less than once per second, and a duty cycle of 54%. So 54% of the time the LED or the signal that comes out will be high, and the rest of the time it is low. And here we can see it's roughly represented 50-50. Example C here, so this timer here, I've used R1 1.15 mega ohms, and R2 I used 100K. And the result that we get is that we work in the frequency of 1 Hertz, so roughly the same as this one. And the duty cycle is 92%. That's why we see the LED most of the time on. And you can see how it's represented here within the cycle itself. And example A, since in example A we can see that the duty cycle is really short. In a stable mode, you have two modes categories of working. You have above 50% duty cycle and you have below 50% duty cycle. So I'm going to set my calculator to below 50%. And the difference in the circuit is, again, you can find this in the data sheet, is the addition of this diode here, which goes between the discharge and the threshold pin. And why it's there and why it does its job like that, it's not relevant for this video. You just need to know that to work below 50% duty cycle, you need to use this diode between pins 7 and 6. So when in this case I have below 50% duty cycle, I'm going to feed the value of R1, which I've placed, and that is 300K. And you can see it right here, two resistors of 150K in series. And for R2 I used 1 mega ohm resistor, and we get again a frequency of 1.1, so it's closer to B, and a duty cycle of 23%. And that's what you see, 23% of the cycle the LED is on and the signal is high, and the rest of the cycle it's off. And you can see now all of this, how it happens in these three timers that I've set up here. Now what would happen if, for example, I would take a signal from this timer and I will feed it into the monostable timer? Will the counter count according to this rate or according to that rate? We can find this out. I'm just going to connect this right now. So I've connected it, and you can see the obvious result, just like when I press this button here. Even though a stable counter provides a constant signal, a constant on and off at a higher rate than the monostable one, still the binary counter will count at the rate of the pulses that are created by the monostable timer here. Now to move on, I will divide this video into two parts. So I've covered the first part that deals mostly with the theoretical stuff and the things that you need to know about these timers. And in the second part I'm going to cover the timers that I've built here, which shows how we utilize this information, for example, to drive servo motors, and also this timer here, which will deal with higher frequencies. So thank you for watching, and I'll see you in the second part.